Well, hello again and welcome again. Now we are going to handle real-time communication. And we are not going to handle the principles of communications, for example, framing or different communications protocol. There are many of them, or bit encoding, byte encoding, message encoding, message framing, and different encoding of messages. This is not going to be the topic here. Here we are going only to see what we have to consider to be able to have communication in real-time systems. What are the requirements for the communications in order to be able to fulfill timings? The first question is, what do we have to communicate? What is our data to be transferred or only signals? There is a difference. We have data flow or we have signal flow. So in both cases, we have a source of the message and a target which is going to consume or requires the message. For example, we are sending from sensors or control panels or operators to some control unit. Or maybe the communication between processors or communication task or application task distributed in different processors, or maybe even in the same processors. Okay, or we have from processors to actuators or audio signals, for example, in control systems. Now, but first, let's make a difference. Data or signal. When we are transmitting data, the message has a content, has some information inside. For example, the speed, the position, the temperature, or much more complex, the summary of the world state of the machine, or the satellite, or aeroplane. Signals, they have only an ID and no data, no contents. It's something like a pulse, saying now, clock. This is a typical case when 1 pulse per second. I hope you remember this 1 pulse per second is a signal which we are using to synchronize the clocks, to synchronize the time. It has no data inside. What time is it? Was a message what was sent before, and now we send now at this time point. The last time is the current time. Tac. Okay. Then in both cases, if we are working with a real-time system, both cases, data and signals, they are time bounded. So we have a deadline, we have a window when we have to deliver this data, not later than this. Or the quality of service is decreasing if we are going too late. And we have a consideration of jitter, how exact do we have to meet the time point when to deliver something, if there is some vibrations in this time point. Okay, now we have to consider when delivering data, we have this time bound, we have this frame, not later and not earlier than this, but this is somehow bigger if we compare when delivering signals. When delivering signals, we have no data, but the time points when the signal has to arrive is very well defined. Maybe we have only microseconds or nanoseconds time to deliver these signals. A very clear signal is the 1 pulse per second because it's going to be used to synchronize the clock in the system with a precision of less than microseconds. Then this signal has to be delivered with a precision of 1 microsecond and a very low jitter, vibrations, sometimes earlier, sometimes later. That's very bad. Here, with data messages, we can tolerate much more jitter and such and these things. Okay, these are things which we shall consider when dealing with real-time communication data or signals. But in any case, we have predictability. We shall know when everything will occur. And in order to achieve predictability, in hard-time systems need communications protocol that allow the communication overhead, delay, and jitter to be bounded. So we have an upper limit and maybe lower limit of time delays, of jitter, of overhead. So we know what is the maximum. The worst case we will require for the communication. Okay. Now next, about what to transmit. We have different types of traffic in real-time systems. The best thing for us, which is what we use in most control systems, is constant rate. So the messages have a fixed side. For example, if you are transmitting the position of the machine, then this format, which says what is the position, has always the same format, always the same size. And we have periodic intervals. So if we are controlling something, for example, the position or the speed of this movement, we have a loop. And this loop has a constant period, a constant cycle, and therefore it's periodic. And this period of time when we are going to repeat the messages is very well defined. And said before, that is the typical case for control applications. Sensors generate data in regular time frames, and the processing has regular time frames, and the consumer, the actuators, has regular time frames too. So, and we are going to concentrate on this because this is our best case. Then we have variable rate. This is, for example, with video transmissions or audio transmissions or commands sent by an operator or something like this. So in these cases, we have variable size of the messages. For example, the commands which are sent by the operator. Maybe some commands are very short, some commands are very long, if they have more or less parameters. Different commands have different parameters. And they have irregular intervals. We don't know when the operator is going to send the next command. Maybe once per second, maybe once per minute, or maybe not today. So we know very little about these intervals. And for example, when we are using voice or video encoding, the size of the message of the one frame of video, for example, depends of the content of the frame. So sometimes you can compress much better, sometimes you cannot compress very well, and then the frame is going to be longer and shorter. Okay, this is a problem when we want to have bonded communication. And this is the case when we are using, for example, streaming of audio or streaming of video or streaming of commands or something like this. Okay. Now, let's talk about the quality of service, QoS, for communication. We have different parameters. For example, we have the bandwidth, the speed of the network, how fast we can send the messages or data, and how fast we can get the data. And here we have to be careful. Sometimes when we are talking about a bandwidth, we are talking about the bandwidth of the network, the total bandwidth of the network, and this will be divided among the number of processing units. If we have many units and a very limited bandwidth in the network, then every unit will get very small. And to make everything worse, maybe it depends of the activity of the different units. Maybe some units are communicating very fast and some are communicating very slow, and this might vary from computer or from unit to unit, and then the bandwidth which you can use from a determined unit can be very different from time to time. So this is when we are talking about the bandwidth of the network. You can talk about the bandwidth of your link interface to your computer. And this cannot be faster than the network, so that is the maximal data rate you can access from the network. Then you have to consider the delays. And this is end-to-end. When you send a message, how long it will take until the receiver will get this message in his memory or in the application which is expected this message. And it depends on software, on hardware, and the size of the network, and the bandwidth, and the size of your message. Then we have to consider data losses. It's almost impossible to have a communication system which will never lose data. So we have to have some statistical value, how much data, how much messages we are going to lose. And this is something important when we are losing data, for example, because of data corruption, then how many messages we are going to lose is a function of the size of the messages. If the messages are very long, then the probability that one data is corrupted in this message is much more higher than if the message is much more slower. Then the probability of losing a big message is higher than the probability of losing small messages. Okay, then we have a jitter. As mentioned before, when we are talking about time and periodic systems, we know when the data shall arrive. And if it is very well defined, a very low jitter, it will be always at the same offset from the beginning of the cycle. It may have a big delay, it might be later, it might be earlier, but this time from beginning of the cycle until the delivery of the data is very constant. If you have a very big jitter, then you will have vibration, sometimes earlier, sometimes later. And this could cause some problems. For example, time distribution is the clear case. If you have a big jitter, then your time control will be having many jumps. If you have a very well-defined jitter, even if the time delay is long, then you can compute this, compensate, and have a very well precision of your clock synchronization. Okay, what can we do? Which techniques do we have to improve this data? Okay, to improve the bandwidth, there is no software technique. This is just hardware. Make a better hardware network. But to improve the delays, there are some things which you can do in software or in your existing network. For example, you can add priorities to delay-sensitive messages. If the network has to handle different types of messages and some are important, you can select the most important messages to give a higher priority so they don't have to wait for the network to be delivered. And then these important messages would have lower delay. But nothing is for free. The not so important messages will have a bigger delay because they have to wait for the high priority messages. Okay, but if we say important is the high priority messages, then we are winning something. Then dealing with delay and jitter, we can create something like reservation of resources. So we can say for this node, you have reserved every second so many bytes or megabytes which you can transmit. So when the time arrives, then the network will be only for this node, and then we can have a very high deterministic system because we know the resources are reserved and the node can transmit in this computed time point. Okay, to handle losses of data, we need handshake or retry and resend. So we have to see if messages are not coming, then we have to say, please send again. We are going to handle these 2 points later because this is an important parameter when we are dealing with real-time systems. They are a very big problem against real-time. Okay, and most time we do use the best effort. No quality of service, just do as good as you can. That is the best effort. And this is a, let's say, quality of service model, even it is not a quality model, where all packets receive the same priority. So all packets are the same, or messages are the same. And there is no guarantee of delivering package. You do as good as you can. If messages are lost, then they are lost. This best effort is applied when network has no configurable quality of service. So you do the best you can. The opposite is you have integrated services. INSEF is the name of this. And this is a quality of service model that reserves bandwidth for different paths, for different nodes, or for different messages, or for different services. And applications ask for the network to reserve the bandwidth on the times and the period they need. And then the network can check, do I still have so much free capacity? Then you say, yes, I can assign this to you, or no, I have assigned already too much and this is more than what I can guarantee. And then new coming messages will know I will not get the quality of service which I am expecting. That is a problem because the first they get the quality of service they request, they get the reservation of the resources, and the ones who come later, they are rejected. Sorry, I cannot satisfy your quality of service requirements. Okay. And now, let's talk about reliability. This is what I said. Data losses and how to increase reliability is a problem for real time. And now, let's see why. Okay, when we are delivering data, we have different qualities. Zero quality, each message will be received at most once. So you send it every message once, and everybody will get it or not. So but you are not going to send it 2 times, so you cannot receive it 2 times, so you will receive at most once. Or if it is lost, you receive nothing. Then the next step is at least one. So you send a message, and if the receiver didn't get it, you repeat. And repeat and repeat until the receiver got it. Then we have a problem. If you are repeating, maybe some receivers will get the same message several times. So the next quality of service is not at least one, but exactly once. So every message will be received exactly once. If it is lost, you will receive again, but you will not get repeated copies of the same message. And then we have a problem. If you are repeating messages and you are sending several messages before you repeat one, then maybe the receiver will get the messages in a different sequence than the sender is sending. So maybe you are sending message 1, 2, 3, 4, and the receiver will get 1, 4, 2, 3, or something like this. And this could be a problem too. So the best thing you can do is receive exactly once and preserve the sequence of messages. Okay, and what are the problems we have? Messages lost, if they are going to be repeated. Most of the time is due to data corruption in the transfer lines. Maybe using radio communications, then the probability of data corruption is very high if you have a noisy system. Even if you are using wires and you have a noisy environment, then some bits can be flipped, then the data will be corrected, and you have to have some kind to check the consistency of the data. So something like like checksums or CRC, cyclic redundant codes, so you can check if the message is exactly the same what was sent. If not, maybe you can correct and it's okay, or you say the message is lost, I'm not going to deliver corrupted messages. This is another thing. Sometimes you can say, okay, I cannot get the message again, then I deliver a corrupted message, and the receiver shall be aware that some of the data is wrong. But that's a totally different topic. The next probability to lose data is buffer overflows. Normally, on the way from the sender to receivers, data is stored and then sent again, stored and forward. And sometimes the receiver has some buffers to get data, to store data before it can be forwarded to the target application. And if we are getting data faster than the consumer can get in, or the router, the switch is getting data faster that it can forward, then the buffers are going to get fuller and fuller and fuller, and when they are totally full, then some messages will be lost. The newest messages can be lost, or you can make it better. The older messages will be lost, and you get the newer. But both ways had pros and contras. They are not perfect. So you are losing data due to buffer overflow. Or the third possibility to lose data is timings and reactions time. Maybe the receiver is busy doing something else, and the data is coming, and it's not ready to get, and the data continue coming, then you lost maybe 1 byte. And if you lose 1 byte, then the message will be corrupted, and then you have to discard the whole message because it shifted. That's a very big problem where you cannot, which is very difficult to reconstruct the data. If 1 byte is just corrupted, then you can try to find what is corrupted, correct, and continue. But if data is missing, bytes are just missing, then you cannot correct this message. It's totally lost. Okay, this is the data corruption, message lost. Then we have another problems, for example, crashes. Every computer can crash, even the network may crash. Okay, the first problem is the receiver crashes. The sender keeps sending and sending and sending until the receiver says, I got it, but the receiver has crashes. So you have to have a timeout and say, okay, I quit. I'm not going to continue sending because no one is receiving. Or the receiver crashes and it will be restarted and it knows which messages arrive already. And then you begin from this point new and you have lost all messages before. Okay, then you have the case the sender crashes. The best case if you send the message it crashes, it will be restarted, and you know what was before, and you don't repeat messages. Or maybe it will be started and send some messages again, and the receiver will get some messages more than once. Sorry. Or the sender crashes and stops sending. Okay, that's another problem. And we can have a similar situation with crashes from the network. If the network has buffers, or if the network doesn't have buffers, it's only a line. When you request a communication, then you get a line, and the buffer will be only at the beginning, at the sender, or at the end, at the consumer, at the receiver. So if the crashes, then you will lose the messages in between. But if the network has buffer and crashes, then we can lose many messages, or messages which was already stored. And if we restart, maybe we can try to resend some messages, and then we can get the problem. Some messages are going to be transmitted more than once. Okay, these are the problems dealing with reliability. It's not dealing with real time, but how reliable is the data transmission. And to be able to have a higher reliability, we will have a problem with the real time. Because, well, I'm coming to this later. The things which okay, just a second. Okay, sorry for the interruption. I made a mistake. My slices were in the ground sequence, but I corrected it already, so we can continue. Okay, we're talking about this. We were talking about reliability. And I mentioned before, to combine reliability and real-time performance is really difficult. Because if we are winning reliability, we are losing real-time predictability. And the other opposite, if we want to guarantee real-time, then we have a problem with reliability. Okay, we can reach both of them only for very slow real-time system and or very high-performance communication systems. But okay, then let's continue. Real-time versus reliability. What can we have? Okay. The biggest problem is what if packets get lost? That's the problem with reliability and real-time. Well, what we do in real-time systems, when packages are lost, we wait for the next round, and then we have to interpolate. Because I said before, with the real-time system, we have most of the time periodic system, and the messages are going to be periodically. And if some message is lost, then we can survive one or maybe two cycles, making an estimation of the data which we are missing. And these are the types of communications. For example, when we are using UDP, communication protocol over internet, it doesn't guarantee the delivery of messages, but it's the lowest delay we can have. Or some time trigger protocols, which we are going to handle later in this lesson. This is what we are going to have most of the time. Okay, on the other side, reliable. We want to have reliable communication. And the problem with reliability is package may be lost in the transmission system, but the receiver shall get all of them. Do you remember the quality of service? At most one, at least one, exactly one. And we want to have exactly one. Okay, and we can do this only if we are able to detect packages which were damaged or didn't arrive. This is a little bit more difficult, and we have to resend the package. Correct is sometimes possible, but not always. And to do that, we have to send acknowledgement, and we have to have some kind of repeat protocol. And that is the protocol, for example, with TCP, from IP protocol TCP, which can guarantee each package will be delivered exactly once. Okay, and what is the problem? In real-time system, communications problem are package loss, and we have to interpolate and make an estimation of what is the current position of the system now. With a reliable system, communications errors mean performance drops, because the messages which are not arrived will be sent again and again and again. So the whole number of messages transmitted will be lower, and the delay for the delivery of message will increase dramatically. So we are dealing with communication performance losses. The communication performance is dropping, and the periods and delays and jitter are going to increase dramatically. The packets are lost. Okay, then how do we do it with reliability? Do you remember the receiver shall get at least once, but let's say we want exactly once. And the next problem, we shall preserve the sequence of messages. Okay, I said before, reliable transmission, we cannot be sure we will never lose the messages, so we have to have retry, resend. And to know what to resend, we have to have something like acknowledgements. So the receiver shall say for every message it gets, I got it, I got it, I got it. And you can see the communications bandwidth will increase because you send a message and the receiver sends an answer, I got it. So at least twice as much messages will be transmitted. Okay, and this does not fulfill the real-time expectations. For example, for periodic messages, if you are dealing with an old message, maybe you shall send newer messages, but you cannot because you are still repeating older messages. Therefore, for real-time systems, you shall be able to tolerate the loss of one or two messages. And in the meantime, make some kind of extrapolation or maybe interpolation and make an estimation of your system. For example, you are getting messages which include the speed and the position, and you are losing some messages, then you can get the last speed and extrapolate what is the current position of your system, how it is moving according to the last speed. So if the dynamic is not very high, then you can have very good estimations until you get new data. Okay, and reliable transmissions and real-time together, as said before, only for very slow processes and or very high performance communication systems. Okay, so is the way how it works. First, I said before, we have to send an acknowledge for every messages. And then we have a dilemma, when to send the acknowledge. When the data arrives at the computing node, the receiver computed node, or when the final application has processed the data. Or maybe when the final application gets the data, but maybe something was wrong in processing the data or the message, and then we lose something. So the most difficult situation is we send the acknowledge only after the processing of data. Okay, let's say we have two computers and they are both communicating in both directions. First, we have to create a synchronization channel. We say, I am here, I want to talk to you, and the answer say, okay, I'm ready to get your data. And then you begin sending data. And here you take the decision when to say, I got the data. Immediately when you get the data or after processing. Let's say in this case we take the decision, we will send the acknowledgement after the processing the data. So you get all this data, you have to merge several packets together for a bigger set of data, and then you can process, and then you can send the acknowledges. I got this, and this. So you send 3 acknowledges, what I got. And then maybe the opposite direction. Now he is going to send the data. He sends 3 messages. It proceeds, and it sends the 3 acknowledges. I got all of them. But you can see this is not really very good, not so efficient. We can do it better. Let's see how. Okay, what are the processing of real-time messages? When we deliver a message, the receiver node has different options. First is to write all messages in a FIFO, and then it will be later distributed to the final applications. The next option is, in this FIFO, we can have priorities. Maybe different applications have different priorities. Some messages shall be delivered first, so the sequence of messages in this FIFO is not first in, first out, but according to priorities. Or the other way is to not store in FIFOs, but call directly the handle function of the final application. Okay, And how to handle this real-time and reliability? Do you remember the communication OSI model? So we have 7 layers, from the physical layers dealing with hardware bit encoding to the application layer. So, and we have a data link, how to encode the messages, a network layer, how to route the messages in the network, then a transport layer, how to forward the messages inside of the applications, together with the session layer, the representation layer, byte indianity, maybe encryption, and then the final application. And let's make a separation here at this point. From layer to the bottom, we have an medium access protocol. When can we send data messages and we will receive data? And from here, from transport layer to the top, we are going to handle at this position the reliability of data, how to handle if we are losing data. Let's begin with the top, this. And let's talk first of reliability. And then we are going to see how, if it's possible to combine reliability with real time. If not, what is the best we can do? Okay. The best thing, the most effective thing is to have something like a flow control at the lower level. I said before, reliability is going to be handled from here to the top, but at this point, let's make an exception. The flow control at low level will be handled here at the network layer. And it works like this. You have a transmitter, you have a wire connection, and you have the receiver. So you are transmitting bit for bit using a shifter, and you are receiving bit for bit. Using a shifter, you combine several bits to a byte or something like this, and then you write in FIFOs, and then you can proceed your message. And then you have a control. And this control is checking if you are getting the data correctly, and if the FIFO has no capacity to get more data, and if not, you say stop, please stop at this moment. And you can stop from one byte to the next byte. So you don't have to continue until the end of the message, and any position you can stop. And this is and this is very efficient, and it is even able to be done in real time if you are getting the data in real time. And you are not going to have losses of data due to buffer overflow here or here. Well, if you have data corruptions, this is another topic. But to handle losses of data due to buffer overflow, this is the best way you can use data flow at byte level, and this is real-time able. So, but difficult to implement. Okay, and it can be something like this. You can send several data, and at any point you can say and stop. And this stop will not be done immediately because it will have a transmission time from here to here. And up to that, you have sent more data. So when you say stop at your local computer, you have enough buffer free to be able to handle all data which is going to come due to this delay, the transmission of the stop signal and the reaction time of the system to stop sending. Okay, and after a while, you send another topic, which you say another token, which you say, okay, I can continue. Please continue, and then you will continue getting data. And this is the time slot. That is from transmitter to receiver. And this is handling data flow at higher level. Now we are here at this data link interface on the upper layers of the communication stack. This is still real-time able, but a little bit more difficult because you have to have bigger buffers to compensate these delays, but you can implement this in the upper layers in the software. The other has to be implemented in hardware. And now, how it shall look like in real time. This is to implement some kind of reliability. The situation in real time can be different. We send these messages, and we send the message according to the time 12:00, 12:01, 12:02, and then we lose a message. But it doesn't care. The sender continues sending, and sending without knowing if the receiver is getting the data. Okay, he got 12:02 and 12:04. and something is missing, and in this thing you have to estimate. Just a second, I'm going to correct this slide. Okay, corrected. I was saying, okay, we lose here a message, but that's not so bad because the next will come, and we have only to, and we have used to span or bridge this missing message. And for this, we can use an estimator. I said before, if you know position and speed, then in this missing message, you can compute the current position and assume the speed doesn't change. So you can continue controlling your machine without a very big problem. If we lose a lot of continuous messages, then you have a problem. But in between, if we get some messages, we can synchronize our estimator and continue working. So it's not a very big deal if we are losing some messages, a few messages. Okay, and now we want to implement reliability. Sorry. Okay, here, yes. Now we want to implement reliability. We are going to do it in the upper layers, in this link transport layer. Okay, and it works like this. The most simple case, you send a message. We are now not talking about bytes. We are talking about complete message. So we sent a message, the receiver, we sent an acknowledge. I got it. Then you send the next, and you send the acknowledge. So you see, you cannot send immediately the next message. You have to wait until you get the acknowledge in order to send the last one. And here you send, you get nothing. And then if it gets nothing, then it's not going to send an acknowledge. It got nothing. So it will implement a timeout. The maximal delay, it can wait until it assumes the message was lost. And then he sends again this last data. And then it says, I got, and it can continue. So you can see the delay from here between messages can be very different. In best case, nothing is lost, is this period. And here you have twice as much this period plus the timeout. And this timeout has to be bigger than this period sending and receiving. So maybe 2 times as much. So from here until you can continue with this data, maybe you will lose 4 times more time than this normal period. So if you are dealing with real-time systems which has this period, then you are lost. It will not work. So you shall have a real-time system with a period at least 4 times bigger than this communication cycle. And then you can compensate losing one message. If you lose this message more than once, then you will not be able to fulfill your real-time requirements. But we can do it better. Before we try to do it better, the acknowledges can go lost too. So you send the data, you get the acknowledge, you send the next data, you get the next acknowledge, you send the next data. He got the data, the receiver. He sends the acknowledge, but the acknowledge went lost. Data corruption or buffers or who knows what. And he realized, okay, I am waiting for the acknowledge, got nothing. So it's waiting at least twice as much this time. And then he sends again this data, D3. And now we have the problem exactly once. We say he shall get the receiver the data exactly once. But here he got the data 3 and here got the data 3 again. Okay, he will send an acknowledge and then we can continue working. But how to avoid this replication of messages? Okay, each message shall have a unique identification. And this unique identification could have, for example, be sending node, sending application, and a counter. So every message sent by application sent by an application on each node will be incremented and incremented and incremented, or something like this. And then, or the time of producing the message with a very high precision, maybe in nanoseconds. And then the receiver, not the sender, and not the network, will be able to see, okay, this ID of message is replicated. So I process already the message 3, and I got it again. Okay, I have to send again the acknowledge, but I'm not going to proceed this message again. Okay, and okay, it will work, but it's not very efficient. We have here a very low real-time performance. So how can we do it better? Let's see. We can send several acknowledge together. So we don't have to wait for each acknowledge to send the next, but we can send several and we can expect several acknowledges together. Okay, for example, he keeps you sending. Here sends package 1, 2, 3, 4, 5, 8. And at this moment he says, okay, I'm going to acknowledge I got already 1, 2, 3. Okay, he knows he got already 1, 2, 3 and continues sending and sending. And let's assume the message number 9 got lost. Okay, then here acknowledge, he will say I got from here to here 7, 8, and 10. 9 didn't arrive. Okay, here you get the message. Okay, we got 7, 8, and 10. And you have sent already up to 14. Then in between 14, you resend the message number 9. And then you continue with 50, 16, and so on. So you have a very high performance. You are sending with the highest frequency you can. But then you have a problem. You shall be able to resend this message. And this message is already very old. It was sent the number 9, and you are here by number 15. So the sender has to have a very big buffer to be able to repeat old messages. And then we have another problem. Here we got message 10, 11, 12, 14, 15, 9, and then 15, 16, and so on. So it's out of sequence. So if you are looking at this, the sequence was lost. Okay, then we have the next problem on the receiver side. So we shall get several messages. Maybe they have an index, and then we shall be able to sort these messages and deliver to the application only messages which are already in the right sequence. For example, here we deliver to the application up to message 8, and then we got message 10. We cannot deliver to the application message 10. We have to wait until we get the message 9 and store all these messages. So we need a very big buffer in the receiver side to store all these messages, to sort, and at this point we can pass the message number 9 to the application, and then we go back and continue from 10, 11, and so on, which is already stored in the local memory of the receiver. So it makes everything much more complex. Okay, now how to keep the sequence? There are two ways. The receiver buffers many messages, and then it sorts before they are forwarded to the application. Or the most simple thing, we can keep sending with high speed, and from the missing message, all messages will be sent again. So here we come up to 8, and then we get 10, and we stop receiving. I sent the acknowledge, I got up to message 8, please continue from message 9. Okay, and then it continues until here, and he gets the acknowledge, I lost number 9, then it sends number 9, and then it shall resend from 9. Okay, 9, 10, 11, 12, not like here, not 15 and 16, all this from here to here shall be repeated. And all this from here to here will be here ignored. So in this case, we have a lower performance because all these messages will be sent 2 times, even if they were already sent, even if they were already received. From here to here, we have to resend. So the performance of this is even still better than this, but not very well. The best thing is if we can sort. But now we have the problem, when shall the application get the data? Okay, here is getting the application with data with a period, with a rate. Then we have a very big hole, and from here we get the applications again with higher rate because we have already all these messages. So the rate of received messages is not constant. So some messages for the application will come with defined distance, then a long period nothing, and then very fast many other messages, and then we continue with the normal speed. So if it is okay for your real-time requirements, that's the next question. Okay, then let's conclude at this point this lesson. And in the next lesson, we are going to see how to implement this reliable transmission communication system. Thank you very much.